Good morning, all. We will be starting in a while as we are waiting for our guest to join.
Hi.
Good morning, ma'am.
Morning.
Good-
Yeah, actually, I
Good.
joined from my daughter's account.
Okay, no
They
issues,
only
ma'am.
use the this Zoom, so that's why.
No issues, ma'am.
Yeah.
So, can we start?
Yeah,
Yeah.
sure. So I can share the slides.
Yeah. Good morning, all the participants. So, the speaker of the today's session is Dr. Monika Agarwal. So, Dr. Monika Agarwal is working as a professor in the Center for Applied Research in Electronics, Indian Institute of Technology, Delhi. She received the BTech degree in Electrical Engineering and MTech degree in the Electronics and Communication Engineering from RIC Kurukshetra in 1993 and 1995. She had done her PhD with the specialization in signal processing and communication from IIT Delhi in 2000, in the year 2000. She was employed with the Hughes Gurgaon from 1999 to 2002, and during 2001 she was a visiting researcher in the Department of System and Control, Uppsala University, Sweden. She has published more than 62 research papers in national and international journals of high repute and conferences, and was also involved in the funded research project. She has been delivered many expert lectures in signal processing. So I welcome Dr. Monika Agarwal for the session today. On the behalf of Manav Rachna, ma'am, I welcome you. So kindly take over the session.
Thank you. Thanks a lot for this nice introduction.
Thank you.
So I share my screen. I
Yeah,
hope it
ma'am, we
is
are able to
visible.
see. Yes, ma'am, we are able to see the screen.
Okay. So today, what I thought is I have started. This is a new area which I want to explore, and I'm also looking for some young researcher to kind of participate in our journey. So I thought I can just talk about this. So before
Ma'am, we are not able to hear you.
Oh, I was muted. I'm sorry for that. I'm sorry for
Okay,
that.
okay.
I just gave started. Thanks,
No issue.
thanks for the wonderful introduction and for inviting me to this webinar. It's always a pleasure to interact with young minds, and I am really thankful to Professor Anita for giving me this opportunity to be part of this series. Uh, I'm today I'm going to talk about something which is quite new and which is trying to hit the market very soon. So this is quantum computing. Before I begin, I just want to know and understand from you, do you understand what is quantum computing? What is quantum? And or what is quantum machine learning? Anyone? I also started working in this area very recently, and I'm looking for some young minds and young researchers to join our team and carry this work forward. So, if anybody is interested in this work, I hope even if you do not know, by the end of my talk, you'll at least understand what is a quantum machine learning, and it is a really exciting area which is kind of going to take the future, and I hope you will start appreciating this. And if you want to join further, you can write to me and we'll be happy to collaborate with you. So what is a quantum? You might have studied the quantum mechanics in your 12th standard, which might be the boring chapter of the entire physics that you had taken. I mean, for me, when I was in 12th, I didn't understand what is quantum and what is relativity and how things were happening there. But that time, maybe my vision was not that big that I could even understand. And also, the things were evolving. Maybe that was the reason I uh, uh, should not give the I should not take the credit from it. What is a quantum? Quantum is something which is making the things faster. So let's just history says that. I mean, when our great grandfathers were studying, they had vacuum tube diodes. When we graduated, we were also studying those vacuum tubes things with us, those diodes and triodes, which were in a glass encasing. I have seen those things. I am not sure that young generation has seen those or not, but they were the backbones of the things that were carried on. Then we went to transistors, which is like a smaller miniaturization versions. Then we went to integrated ICs. I mean, those you still.
Hello, ma'am, your voice is not audible. Hello, hello, ma'am, your voice is not audible.
I think there are some internet issues. Sam will be joining soon.
Dear participants, there is some network issue. She is being joining shortly. Wait for 2 to 5 minutes.
Hi, I'm sorry, I just got disconnected. I had some network issues. So am I audible now?
Yes, ma'am, you are audible.
Okay. Can you just tell me till what time I was like audible and
Ma'am, you have time. You
okay. I can just start maybe again.
Yes.
So what I was telling you that the way things are moving in terms of our the development, we started with a vacuum-based transistors and diodes, which were big transistors and diodes. And as we moved on, we went to transistors, ICs, microcontroller, FPGAs, DSPs, whatnot. These days, we have so many processors, and each processor has its own specification to do certain tasks. These days, people are also designing some processors which are AI based, which can implement all your artificial intelligence, all your CNN, DNN in a much faster way. So that is the way things are moving ahead, and we are going for a miniaturization. But after AI, what is going to happen? That is what is a question, and the future is quantum. Now, what is a quantum and how is it going to evolve and how is it different from a classical computer? That is what we are going to understand today. So what is a quantum computing? A quantum computing is basically, uh, you know, uh, it's something, every atom has a structure in it. And every atom, if you break it, you have subatomic structure. You have electrons, you have proton, you have other things. And electrons revolve around the atom. So that basically the spin. So electron has two kinds of motion as our earth revolves around the earth. So similarly, electron also has two kinds of motion. It revolves around the orbit and also it spins. So those two aspects of it we kind of study together. So this basically happened something like that. So the people said the light has a wave-like structure. So so that's what we know. So the light is a wave-like structure and it moves ups and downs like a wave. Then people also said that light is a photon, a particle-like structure. So light, and there was a debate going among these researchers, which debated about the existence of light and the behavior of light. There was a time when the people were saying that the light has a wave-like structure, and then there was a time when the people were saying the light has a photon-like a structure. Now, in reality, now we know that light exhibits both the properties. It has a photon-like structure, which carries the energy into it, and that is what the quanta is. It carries a quanta of energy. That's what the Einstein said. It has a quanta of energy. That's what the name came, the quantum is. And it also has a wave-like structure, which varies with the time. So all this combined together, a particle can have two kinds of a structure at the same time that gives So basically it's just two structures that we have together and they coexist. That is what is important, and that is what people are exploiting to kind of define what is the quantum is. Now, what is a quantum computer? Quantum computer is just a simple computer, as a simple device, I should say, or a machine, which uses these properties of quantum physics and do certain operations. Now, what are those properties and what are those operations? That is what we let us start. So when we talk about quantum, when we talk about a classical computer, so what is a classical computer? What is a minimum unit a classical computer has? The minimum unit that a classical computer has is a bit. We all know it's a bit. We understand a bit, and bit can have two states, 0 and 1. It's like a switch that I'm switching it on or I'm switching it off. So it can take only two states. But in practical life, that may not be there. See, when so it is so the state of a bit is binary in nature. But if I ask you a question, so do you always have a binary answers? When I ask where were you, why didn't you, are you late? You will not say that, yes, I am late. You will start giving me an explanation with it. So whenever we do something, we always have an explanation attached with everything. So we don't live in binary states, but we have many states in which we live at the same time. So that is what a quantum computer exploits. It is so the fundamental unit of a quantum computer is not a bit, but is something which is known as a qubit. So that is a fundamental unit of my quantum computer. Now, what is a qubit? As I just said, so basically it is something which says that you can either be in state 1 or in state 0 at the same time. That is what I am. I am half in and half out. I'm at home, so I am half of my mind is present in this talk, and maybe presently 1/3 of my mind is at my door that somebody's ringing the bell. So we always live in two states at the same time. So that is what a quantum bit is, a qubit is. So it tries to represent something like a state that, so it is unlike my classical computer where I had only two states, 0 and 1. A quantum device has more than one. So it can exist. It says that you can exist in two states at the same time. So how do you represent it? So you have an excited state. So if you talk about a single qubit, you have an excited state, which is represented by this letter. So this is known as a cat1. And this is the ground state, which is represented as this letter. So these are the two states in which you can be into this. This is unlike the classical computer, as I said, that classical computer, you are only in a 0 state or in 1 state at a given time. So what do you mean that you are in 2 states at the same time? It means that you have a superposition. Both the states are linearly combined, and that defines your present state. So this is your quantum qubit is, which is a linear combination of these two states, or you say the superposition things of both the states simultaneously. So this diagram actually explains it well. So you have two states. So one of the state is actually, my cursor is visible.
Yes, ma'am, it is visible.
Okay. So this is a 0 state, which tells me that I am at a ground state, and this is the 1 state. My classical computer bit can be either here or here. But when I talk about qubits, it can be, so this is a sphere that I have drawn with a complete complete thing, and my qubit can take any values on this sphere. on this sphere. So you see that the possibility that a single qubit has, it has so many possibilities around it, where my classical computer only provides me two possibilities. So that's what a difference is. And this actually explains my quantum qubit. Now, this is a single qubit. And so if imagine what is a multiple qubit are going to do, we'll just come to that. So this is my single qubit representation that I have. So using this single qubit, if I define my computer, that is what is known as a quantum computer. Now, because I again want to spend some time on it, because this is quite important concept. When I define my classical computers, what did I do? I use these single bits and define some operations. I define my NOT operation. Okay, so the bit is in one state, and now I want to have a NOT gate. So the NOT gate will make the bit 0 to 1 and 1 to 0. I define all the gates. I defined all the digital electronics based on that, and which resulted into my computers. Am I right? Now similar things, what I'll do is I'll do on quantum bits, qubits, and define my all operations. So now as my NOT gate was very simply defined in case of a binary bit, I require a simple analogy to define my NOT gate. I define my another analogy to define XOR gates and all the gates. So basically, what is a quantum computer? If I say that, so quantum computer is actually circuits of which takes qubits as an input and give qubits as an output. So this is what my quantum computers are. Now, what is the advantages that I am going to get with these qubits? Because see, simple. The advantage is very simple. Now, in the previous case, I had only two things to represent, but now with the single qubit, I can represent the complete sphere. I can represent my positions in the complete sphere. So I am going to kind of get the advantage because I'm going to the real situation. See, it is towards, we are going towards more real behavior to represent. Now, qubits gives me a tool to represent the real behavior in real sense, and I am able to represent that now. So that is the major difference between the classical computer and the quantum computers. That the quantum computers gives you another dimensions they add to your system, and that because it is not only two states, it is combination of two states using a single bit, so which can be exploited by the researchers. And that is what people want to do and exploit, so that they can define better and better solutions to it. Let's just understand more into this. What is the difference between the quantum computers and the classical computer? So suppose you want to do now this is a very device which has been designed to do my multiplication. Sorry, my sophisticated calculations. Now, if you do a simple manipulation, so this is an overkill system. Because, for a simple manipulation where you have simple multiplications, which can be done by a simple classical computer, say in, it's just an example for two numbers which I have taken. So it's a 2048-bit integer, and I have just wanted to multiply these two bits of integer. A simple classical computer takes a very little time. But if I do the same operation on a quantum computer, I require more time. Why do I require more time? Because a quantum computers will take you in a larger span. And you need to search out and then reach to the solution. So it is designed in such a way that it solves the problem in a expanded form. But whereas if you want to do a factorization, which is kind of a very important aspect as we go further and further, it takes very less time. So this was an impossible problem, that if you want to factorize two prime numbers, you factoring a prime number was very difficult if the number of bits are increasing. So that is the reason people were designing those encryption codes, RSA encryption codes, and based on that, the prime numbers cannot be factored. You do not know how to factorize the prime numbers, and it will take billions of years. And those billions of years, the system, you can't hack that. But now with quantum computers, that is kind of things which is going to be changing, and I can do the factorization in simply 8 hours. Because I am exploring more possibilities over here, and that is why I can solve the problem in a much simpler way. So this is the power that quantum computer has, and it can give you many solutions which were not possible just because of the computing power. So it is actually a computing power. But a computing power, suppose I give you a more computing power, definitely you can do more. And it is up to you. How do you want to use that computing power to get the more solutions for you? So this is a list which kind of differentiate between the classical computers and the quantum computers. The classical computers, as I said, it uses only normal bits and bytes, whereas the quantum computers use the qubits. The normal bits like light, you say it's a switch and on and off. It's only two state. Where quantum bits, it's a superposition of these two states. So you can be half on and half off. That's what happens, when you are in the class, maybe in presently also, you may be half in my class and half may not be. So that's what our present state is. And the qubits are basically representing that. So there are, many such differences that are there, which kind of, so basically the classical, it's a quantum computers is actually going to use those principles that are there, which are making it difficult. I think I'll just go ahead, and these are just difference that I think you might have understood by now. So how the quantum computer works, let's just understand that. So basically, it uses two principles of entanglement and superposition. So superposition and entanglement, this is what I'm going to tell you. So superposition, I think I have explained you a bit. So that is what a superposition is, that I can be in a state 0 or I can be in a state 1 at a given time. So that means that I am in a state of superposition of two bits. Now, what is an entanglement? And so what do you understand by entanglement? So entanglement is actually, again, a phenomenon. That was, when Einstein discovered that, he said some spooky behavior of the bits. That's what it was. Okay. So basically, if you understand an electrons which revolve around the atoms, it has a spin. And if there are two electrons which are revolving around it, the spins are compensated. So if one revolves in one spins in upward direction, the other will spin in the downward direction, because in a ground state, in a normal state, you do not have any spin that is present over there. There is no extra spin in the grounded state that the electrons have. So basically, the spins in the electron is always neutralized. So that is what an entanglement is, that if you know the spin of one electron, you can understand the spin of other electron. So this is just like a correlation property, which can be elaborated in this way, that I can I know what is the spin in one state, and I can understand using that the spin in another state. So this is the same thing that we do sometimes. Suppose, so basically this is actually the correlation. It is nothing but the correlation between the states that we have. So let's just take an example and then try to understand this. Suppose you are hungry and you want to order the food, and you ordered some two things for you. One is a hamburger and one is a hot dog. And then what happened is, the man is on the way and he delivers the boxes for you. So he delivers two boxes, and they were packed in such a similar way that you didn't know what it contains. what it contains. So there is a probability that each one of them will have one of them will be having an hamburger, or other will have a hot dog. What will happen is, so if you do not know what do you do? So if you open one and saw that this is a hamburger, you'll understand that the other is a hot dog. So these two states are entangled states. So there is an entanglement between these two states that is always there. So there is a possibility these two orders. But what if you and your friend has made an order and the boxes were delivered? So the boxes may not be physically close to each other. The boxes can be physically apart, but still they are entangled. You know the behavior, that if you know that one box contains a burger, the other will contain the hot dog. So that is what the entanglement is. The physical separation between the bits is not there, is not important. They are still correlated. So this is what the entanglement means, and this is like one property which is being kind of used very much in designing more and more operations on the qubits. The superposition, as I just said, it says that the bits can exist in two states at the same time. So this is how you write your current state. So this phi is your qubit, and you say that you are in state 1 or state 0. State 0 explains your ground state, and state 1 explains your excited state. You are in both the states at the same time. You are in the superposition of both the states, and alpha 1 and alpha 2 is the probability, is a constant factor by which you kind of represent their possibility. So it is actually the probability of being in state 0 and the probability of being in state 1. So that is what my alpha 1 and alpha 2. So as we understand, it's a complex numbers. They can be a complex number, and their mod square is equal to 1. So basically the mod of alpha 1 square is the probability of being in state 0, and mod of alpha 2 is the probability of being in state 1. And as we know, the probability can be always added to 1. So this is what you get, that mod of alpha 1 square plus mod of alpha 2 square is equal to 1. This kind of represents my superposition of two bits. Another important thing is the quantum uncertainty. What is the quantum uncertainty? It is actually Heisenberg's principle of uncertainty that you might be remembering. So what was a Heisenberg's principle of uncertainty? Anybody? So Heisenberg, yeah.
Yeah, ma'am. The position and the momentum cannot be measured simultaneously.
Correctly. So there is a relation that uncertainty in the position and the momentum is limited. So that's what the same thing is applies over here. Thanks for the answer. I know that I'm glad that you are listening what I'm saying. Well, many times in the online mode, you do not know what is happening because you are on your screen and you are only teaching to yourself. But thanks for the answer. So that is what my answer.
Thank you, ma'am.
Thing is that you cannot understand your position and the momentum of the particle at the same time. So all this together kind of explain my behavior about the quantum things. So as I said that I have a single qubit, I may be having more than 2 qubits. So if I have more than 2 bits, then I have more number of states over which I kind of work with. I have 4 states, isn't it? So 2 bits together represent 4 states. So I have four states, and my 2 qubits together represent my 4 states. And similarly, if you have n qubits, so you have 2 to the power n Q states that represents your qubits. So basically that's the thing. So the way things are, so 2 bits represents your 4 levels at the present, but now my 2 qubits represent my so many states in this case. So this 4 qubits these 2 qubits are represented by this vector, which is contains the probability of each of the state that occurs over there. So this alpha 00, alpha 01, alpha 10, and alpha 11 are the measures of the probability of being in state 00. Both the qubits are in state 00, 01, 10, and 1. So this kind of gives me more rooms, and now you can imagine. So that was a sphere, and now you can imagine you are moving to higher and higher dimensions, and you are trying to represent more and more things. So that is what it's happening. So when the
Excuse me, ma'am.
Yeah.
Ma'am, can you give an example of physical meaning of states? What is state? What a state is? Physical example.
Okay. Physical meaning of a state. See, okay, I just give you. See, so the physical meaning of a state is, suppose you have an electron, and the electron goes, you give an energy to the electron, so electron goes to a higher state. Now, in that process, when you give the energy to the electron, it can be in a ground state or in higher state. It can be in between anywhere. So that is what a state is. So you can be in more than, so at a given time, you can be in the more than one state. So this example, I think if you yes. So this diagram, Bosch sphere, explains it in a very nice way, that you are in a state 0 or state 1. A classical computer tells you that you are a light switch. You either is on or off. But the quantum computer says that you can be in more than one state at the same time. It means that I can be in a state where my switch is half open and half closed. Maybe 3/4 open and 1/4 closed. See, okay, another give you an example. See, when you have a signal, you kind of sample the signal. Okay, you have a threshold, and you say that if it is above the threshold, it is that level, and if it is below the threshold, it is that level. But actually, the signal can be anywhere. So it's a continuous signal. So quantum, in a way, represents your continuous signal. I'm saying in a very layman's language that it is a continuous kind of a data, which is the quantum is representing. So you can be in any state. You can be in a you are receiving a voltage from 0 to 5 volt, isn't it? And that is what you say, that if it is a 0 volt, it is a 0 bit. If it is a 5 volt, it is 1 bit. But it can be anything between 0 to 2.5 is your 0, and 2.5 to 5 is your 1. So that is what your quantum says, that why can't I just say anything between 2.5 to 5 is another state? I can be in a combination of 0 and 1. So that is what my superposition. So basically you have two states. That's what the superposition tells me, that you have two states and you are in, you have these two states, and you have two states, zeros and 1, and you presently are in superposition of both of them. You have certain portion of that, alpha 1 corresponding portion of 0 state and alpha 2 correspondence of 1 state. Is it clear?
Ma'am, in case of light, what will be the state 0 and 1?
Okay, in case of a light, see, so light is the energy. So what do you understand? It's a wave. It's a wave-like structure also. So what do you understand by okay? So what do you understand by light being 0 and light being 1? that you are.
Polarization, horizontally polarized, linearly polarized. Hello.
Yeah.
Ma'am, yes, I have studied that it can be horizontally polarized or linearly polarized.
So that is a polarization of a light. Suppose you talk about the energy in the light. So it's a quantum of energy that you have in the light. So you have one quantum of energy, so which makes it that you have an energy 0, or you have an energy of 1 quanta.
When 0 quanta energy, is it right meaning?
So there is no energy.
Physical meaning.
So there is no physical meaning to it. I'm just trying to explain you. There is no physical meaning attached to it. So it's one quanta of energy that you have. So when you go from a ground state to an excited state, when a particle moves from ground state to an excited state, it has a trajectory that it follows. So that is what a trajectory that it follows, and that is what explains you that it can be in any state. When you measure it, you either measure 0 or 1. You do not measure in between. So when you so basically there is another catch to this, that when you take a measurement, of these qubits, you have either 0 or 1. You do not know what is in between. But it can exist in intermediate state also, which is a superposition of these two things.
Yes, ma'am. Thank you, ma'am.
Okay. So that is what my superposition and things, and that is how I represent. So when you have these 4 qubits, you are existing as 4. You are in the 4 state, and you are in a superposition of these 4 states together. So basically, it was a Shor's algorithm that was designed, and what he said that in long back. So that there are 2 algorithms which are very famous in quantum, and one is a Shor's algorithm. Those who have read, maybe they might know, and one is a Grover's algorithm. The Grover's is an Indian person, and I'm very happy to say that he has graduated from IIT Delhi, and so he has designed some algorithm for the quantum, and these form a backbone of quantum the quantum things into it. So what is that? Suppose I ask you that, okay, so what he did is he did a prime number factorization. Suppose I say that 7, you have a number 7, and can you do its prime factors? A number 19, can you do its prime factors? You will be able to do it very nicely. But if I say that if you have a number 2, 3, 4, 5, 6, 7, can you do the factors of that? You will take some time to do it. So that's what the prime factorization problem is. And that's what the basic bond of our encryption algorithm, as I just said. And what Shor did it that he used those quantum algorithms and could show that these numbers can be factorized in a much quicker way, and you can represent, you can factorize a number in a given time, and the things started working from there. This algorithm is kind of a breakthrough, and this RSA is kind of a public key encryption algorithm, which started working and breaking out, and people had to design. People now, when the quantum computers will come, so your encryption is becoming a threat now. So you need to design new algorithms so that your communication is secure. This is even helping is, so though I said that the quantum is making my encryption at a threat, but it is also helping it out in designing my drugs. So the penicillin drugs, when we want to design the drugs, we need to try out various combination permutations, and then only precisely we are able to find out the solution. In a classical computers, it is very difficult to do all those manipulation. So basically what quantum is doing, it is giving you more options to represent your data, and with that in a lesser number of bits. So I hope that you have understood. So the binary bits are only 2 poles, whereas the qubit is a complete sphere. So now using a sphere, I can have more options to represent. Now, as you have more options to represent, you can do faster and some things which is possible in the real time. That is what is happening. So these days, people are talking about quantum in many kind of solutions which were looking very difficult in using the classical computers, because the number of bits were increasing and the classical computers were like having it difficult to handle. So it can be like a drug designing, the traffic optimization, planning, many other things, finance. People are kind of to use these boost and designing some algorithms with. So there are some things. So though I said that quantum is good, but there, as I said before, some things which is good only in the classical computers, and like my multiplications. If I start doing multiplications, the quantum will not be able to do it. It's something like that I'm teaching my PhD students. And if I ask them to solve some 10th class problem, they may not be able to solve, but they still might be good. So the quantum computers are very good if you talk about very computer intensive, in computational intensive problem, but they are not good if you talk about some very simple mathematical problem. So visualization, video conferencing, they may not be good because they are not very computational intensive problems that we solve with. Whereas they are very good if you talk about optimization, where you have larger data to handle and more options to explore, because it gives you a more representation, and then you can do it better. That is what. So basically, this chart is it's very good, explains you some problems which were very difficult for the classical computers could be solved easily by my quantum computers. But this purple portion which is outside this gives me that it has given me a leverage that I can have more solutions. I can create the problems which have more solutions. So it is something like that. Once the technology is evolved, you try to use it to define more solutions. Like I work in 5G also. So as I said that in the 4G, when we started, we never thought of Uber and Ola, I mean 10 years down the line. But now it's part of our life, because the technology has advanced. We have all the net at our place and we can do various things. So we get more and more solutions around that. So similarly, the quantum is going to be there, and it is might help us in their defining more and more solutions to the problem for the betterment of the life. Okay, so presently we do not have a very good quantum computers. We have very small size quantum computers practically, which is say 66 qubits, but it could perform some tasks which can be so this is something which I just took from internet, that it solves the sampling task in 1.2 hours, whereas the powerful supercomputer, where the classical computer would have taken 8 years. That's the analogy that you have. So we do not have a very big hardware at present, but still when the hardware will come, things are going to boom, and we are going to kind of go further and further and kind of make our life much simpler. Okay, this is what I wanted to say about the quantum computer. So I hope this is clear. Any doubts? Now, I think how much time do I have? I'll try to give you analogy what I have in present. I have some of the maths, but I think I can skip that. So basically now what we want is, so another thing is that the machine learning is kind of a very difficult task, and we all are working towards it to design better and better solutions for our day-to-day life that we have. And as we are going ahead, we are getting more and more data. See, presently when the machine learning was invented, we had small amount of data and digital data, but now digital data is kind of everywhere now. Thanks to COVID, even everything is going digital. Even I would have loved to come and give the lecture in person, but it is happening in a digital way, and you have a recording of it. So the digital data is enormous. Now, a classical computer to handle this amount of digital data becomes very difficult. So what we need is, we need to design ways such that the quantum computer can handle it. Because quantum computer is a solution to this, because they can handle larger amount of digital data. I think in this 2 days of workshop of AI, you might have understood that artificial intelligence provides good solution. Your ANN, CNN, and DNN, whatever are the architecture of these networks that you are using, they become more and more better if you have more and more data to train with. Now, if you have more and more data to train with, you require better systems. You require supercomputers, workstations, but they also have a limit. I run the algorithm for 10 days and then get a solution. And then I started, if I get more data, it might become 20 days. It is increasing exponentially. So how do I handle that? So the solution is the quantum computers, because I can handle that large amount of data using the quantum computers. But now the problem comes is that how do I represent that data that I have of my real data that I have in a qubits, because quantum computers use qubits, isn't it? So how do I kind of understand that qubits and try to represent my data in that format? So basically, let's understand. So people are designing methods by which they can represent your data that you have into the qubits, and in a very compact form. So basically, if you talk about the image is so there are few methods by which, so how do you represent an image in a classical computers? You represent as an RGB, you represent red, green, and blue. You have other format, HUI, and many others. So you require some, each format has certain bits to represent. Now, can I represent this image as a qubit? So if I can represent this digital image as a qubit, I am done. I'm able to use my quantum computer understanding and do further. So for that, so the people have designed certain ways of doing it. I will not go into the details of that. So there are 3 methods which I thought I'll cover. So one is Cubit Lattice. And so basically, there is a flexible representation of a quantum image. So I'll go to the flexible representation in the, okay, just to make you aware what is happening. So what it does? So basically, it represents your image. So image is what? So if you talk about RGB gives you the color, but color is actually your it's a color. It's a continuous variable. Why do I need to go to the RGB mode? So what they assume is that, sorry. What they assume is that, they assume that your color can be represented as a qubit, where your theta, you just imagine that you have a light which has certain frequency, and that frequency is the color of the pixel. I mean, as a light of a what is a color? Color is actually given by the frequency of your thing is, so your light is. So that is what a qubit is. That is what a qubit is. So qubit, you try to represent the pixel as a function of that frequency. And because you kind of have that positions also into the place, you kind of use that information of the frequency as well as the position to kind of completely represent your image. So basically what I'm trying to say that there are various ways by which you can represent an image as a qubit. Once you're able to represent an image as a qubit, what you need to do is you need to define algorithms on those qubits. So that is again a research area where people are designing algorithms. So designing a NOT gate, designing a XOR gate on qubits is what people are doing. And the way we have done the Fourier transforms and other things. So that is what the philosophy is, that how do I design those algorithms and work over here is. So that is what people try to do over here, and each representation has its own merits and demerits, and it gives me the different aspects of the image that I have. Now once I have kind of done this transformation, then I can do the similar Fourier transforms on a qubit image and get the similar kind of features that I have. Which kind of I mean, the beauty of the quantum is it saves my time that I have. I am just skipping that because I think I'm running out of the time. So what is quantum neural network? So the quantum neural network, I'm just going to give you an analogy for this. It actually takes a qubit as an input. Now as a neural network, it has various layers into it. So each layers of this is actually the gates that you have, the quantum gates that you have. And now as a see, if you talk about the problem that the quantum bits, it's a continuous thing, whereas your qubit is a continuous kind of a state, whereas your digital bit is a discrete state. Now similarly, your gates are the circuits. Like when I said NOT gate, XOR gate, they are the basic components of your computer. Each layer has a perceptron over here. Similarly, now what is a quantum perceptron? That becomes a challenging thing, because in a quantum you cannot so there is something which says that you cannot copy one bit into the another. So in a quantum qubit, the equality thing does not exist in a way. So that is what is known as a no cloning theorem, that says that I cannot copy the things. So you require certain further operations to copy your bit into another bit. Now those layers are kind of made of a inner circuit form, and which does the quantum operations using bits, and then in the end you make a measurement. So your quantum neural network actually a conjunction can be seen as a conjunction of your quantum bits and your quantum circuits, and which have been so what do you train over here? You train those parameters of your quantum circuits to make your operation work in a much faster. And this as a so basically people are also thinking that why can't I use these tasks on a classical computer? So people are evolving these algorithms and kind of working further to make these quantum computers. So the hope is that when the quantum computers will come, people will be having these algorithms and will be able to get good understandings of our things, and we'll be able to do our systems much faster. I think that is what I wanted to say over here. Any questions that you have? I hope I have not taken more time.
Hence, you can ask your questions or you can write in the chat box.
Hello, ma'am. Hello. 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 Hello.
Hi, I got muted. I'm sorry. Yeah, hi.
Hello. Ma'am, can you refer some books for quantum computing?
Okay. So instead of a book, if you look at some lectures, they'll give you insights. So there's a lecture by what is his name, Umesh Arzani, and so he has explained very nicely what is quantum, all the operations very nicely. So there are a couple of good video lectures that are there. I can share those links with you, maybe Professor Anita, and then she can forward it to you. And also,
Okay.
I don't remember offhand, but there are some good books, so which you can also, so they are freely available on the net, so you can just use them and understand them better.
Okay, ma'am. Thank you.
I didn't go into too much of maths because I was not I couldn't understand how much the grasp is in this course, but if somebody is interested in working this area, I'll be happy to collaborate, and please write to me, and we are actually looking for some students to work in this area.
Okay, thank you, ma'am. Thank you, ma'am, for your fabulous lecture. Your lecture was very interesting and interactive, and I hope all the participants have gained the valuable knowledge from it. I thank you once again on the behalf of Manav Rajna, and be sure that we will be connecting with you soon for more lectures. Thank you very much.
Thanks a lot. It's really privileged to be with the group, and
Thank
I'm
you.
really happy to see you have so much audience till the end of the lecture.
Yeah,
That's
yeah,
really
ma'am.
great. Thank you.
Can you
Thanks a lot.
please turn on your camera for photo?
Actually, I my bandwidth is a bit low.
Okay, okay, no issues.
Yeah.
Okay, ma'am. Thank you very much, ma'am.
Thank you. Thanks a lot.
Thank you. Participants, we will be joining at 2:30 for the next session. Thank you all the participants for your patience hearing, and we will be joining at 2:30. All the participants, please kindly fill the attendance. The link has been shared.